Hello, friends. Jim here. Welcome to Science Talk. Well, here it is. Some of you have been inquiring about this. So, this is a lengthy video, but I'm going to talk about what the current situation for polar sea ice in both the Arctic and Antarctic regions are as of the 26th of October, 2023. So, let's get to it. First, we'll look at what's happening around Alaska, and the figures that we'll be showing you with respect to Alaska are courtesy of our friend Rick Toman, who is at ACAP. And ACAP, as a reminder, means the Alaska Center for Climate Assessment and Policy. So this first figure, we're going to look at the combined daily Chukchi and Beaufort sea ice extent each year from 1979 to 2023. With the past 2 years, the record low year of 2012 and the 1991 to 2020 smooth medium highlighted. Okay, the 1991 to 2020 median is this thick black line right here. And median, of course, means that 50% has more ice extent, 50% has less ice extent. 2023 is indicated here in blue. So the minimum for the sea ice in 2023 was reached here about 2/3 of the way through the month of September. And 2022 is this one here in red. So you can see, if you look at starting over the summertime, which is pretty much minimal, it's the oceanic springtime heading into the oceanic summer, which is basically September or so into early October. The 2 years are pretty much the same, and then look what happened in 2023. Massive drop off. So the sea ice extent in square kilometers, look how low it went. We're talking about what, 150,000 square kilometers or so? 2012 is this dash tan line, whatever, and that was even lower. So for the Chukchi and Beaufort Seas, this is the second lowest year. Okay. And of course, when you're watching these videos, you're always free to pause at any point and, examine these figures, more detail if you're so inclined. Sea ice near Alaska reached its minimum extent on September 20th, about 2/3 of the way through the month. The combined ice extent in the Chukchi and Beaufort Seas dipped below 200 square thousand kilometers for only the second year in the 45-year satellite era. Probably much longer than that, with only 2012 having lower extent, as we just discussed. Ice extent was near average for the two combined sea through mid-July, when above average extent in the Chukchi Sea offset below normal extent in the Beaufort Sea. Thereafter, extent dropped dramatically, remained second low from late August through most of September. And we see that. It only started in 2022, it started picking up, beginning mid-October. The data still needs to come in, but as to see what it's doing, but it's the second lowest extent for these two regions. Okay. National Weather Service Sea Ice Program, sea ice concentration for September 23, 2023. Sea ice concentration is not to be interpreted as ice thickness or ice volume. That's an important point. It is how well packed or not the ice itself is. Meaning, do we have a bunch of, ice flows 2 meters across that is separated by 3 to 5 meters of open water, or we have it all rafted together? That sort of idea. So when we look at this scale over here, and we'll get to the rest of this caption in a moment. Okay. When we look, let's just start with the red. Red is 9 to 10 tenths, meaning it's pretty packed. Orange is 7 to 8. Yellow is 4 to 6 tenths. And then blue is light blue. Yeah, this one here is 1 to 3. And then this is less than 1/10. So in other words, we're starting to get into lots of open water, a little compaction, more compaction, a lot of compaction, and this is pretty much you can walk across the thing. Kind of a rough way of trying to get this across. For low values, the ice will be found as individual flows separated by a lot of open water. Higher values indicate ice rafted into each other. Right? Think of it being able to walk across it. The long distances to ice, Kotzebue to Kolyuchin Bay, Utjakvik to the various spots where we see the sea ice, Kaktovik, right? Long distance ice means that any strong storms that come along in the next several weeks have the potential to produce high seas due to extremely long fetch across open water. Right? This is open water. Fetch is when wind blows across the water and creates waves and that kind of stuff. So you got open water here. Basically, you're vulnerable to increased storm events. That's basically what that is getting across. Now let's look at the minimum sea ice extent in the Chukchi Sea from 1979 to 23 with an estimated of the time variant median. That's indicated by this black line. And we can see that there has been a steady decline over the last 4 decades. And we can see how, now this is just looking at the Chukchi Sea alone. And we can see that the square kilometers is well below 100,000. Excuse me, almost to zero. These are yearly, averaging for the whole year. Losing the ice. Chukchi Sea is close to joining the peripheral Arctic Sea, like the Bering Sea and the Sea of Okhotsk, where sea ice is seasonally present, but no longer a year-round feature, which shows a decrease in the minimum extent since the early 1980s of about 98%. Sea ice extent in the Beaufort Sea has been below average the entire melt season. This was perhaps not unexpected, as sea ice thickness near the end of the freeze season was well below the recent year's average. However, record warmth across the eastern Beaufort Sea and adjacent land areas during the summer and a couple of months of very warm water being discharged into the southeast Beaufort Sea from the Mackenzie River surely played a role in pushing the ice extent much lower than in past several years. So you're introducing warm water being discharged from the Mackenzie River as a likely factor. Over sea ice extent. So we're looking at 1979 and 2023. the minimum extent and dates. Okay, now this is not this is just simply points. So basically, they color coded by the decades. So the dark blue is the 1980s, the light blue is the 1990s, green's the 2000s, orange the 2010s, the red 2020s, and the stars 2023. So what they're plotting here is at what date the minimum occurred and what the minimum extent was. So we're seeing here that for 2023, the minimum occurred on the 20th, and as we discussed earlier, it was below 200,000. Here's 2012, when it had the lowest ice extent ever for the Arctic. It also occurred very early, like about September 2 or so. And you can see when you look at the 1980s and the 1990s, you can see that the ice extent is basically pretty much near 600,000 square kilometers or greater. And even into the 2000s, the early 2000s, we see, ice extent in, greater than at least 500,000 square kilometers. But what happens towards the end of the 2000s, like 2009 here, 2007, 2002 also here, but we start seeing it starting to come down. And then when we get into the 2010s, we're seeing it drastically dropping below. Basically, starting with 2014 or so, sea ice extent greater than 500,000 square kilometers is a thing of the past. It's getting less and less ice. Very interesting here. It's also interesting that in the first 3 decades, right, 80s, 90s, and 2000, is where we see the latest dates for when the minimum was reached. And the minimum was reached with a very extensive sea ice extent. Interesting here in some dates here, 80, 81, we had the minimum sea ice extent occurring in August, meaning we had cold conditions, and the freeze up started right away. Freeze up started right away. Do the same thing here for the Chukchi. Okay, same color coding as in the previous slide. Once again, we see that the greatest extent occurs in the 80s and 90s. A couple interesting points here in that looks like 1990, 93, and 98. We had some years where it was below 200,000 square kilometers. And even into the 2000s, we see some years that had a minimum of ice greater than 200,000 square kilometers. But starting in the 2010s, look what happened. Not a single one in the 2010s, and with the only exception of 2021, even in the 2020s thus far, all is below 200,000 square kilometers. It's as if someone threw a switch. And you notice this is from NSIDC data. As was this one here as well. And then ACAP, Rick do their analysis of that. Okay, something of note that I wish to mention. So this is me. Less and less of the precipitation that falls during autumn and winter in Alaska is falling as snow. There are increasing events of freezing rain or rain that falls and not snow. This is especially true for the month of October. October is the month where there is the greatest disparity between historical trends and current trends. In other words, if you look at Alaska and you look at, the historical average temperature, and then you look at the current historical average temperature, the greatest difference is for the month of October. In other words, October is the month that has seen the greatest warming. Much of this is due to the warming Arctic Ocean that keeps the Chukchi and Beaufort Seas open, not freezing up, allowing the heat to diffuse through the atmosphere. And then we get the freezing rain. There is a trend of decreasing snowfall in the Arctic overall, such that by 2100, snowfall in the Arctic will be a thing of the past. I did a video on that. I'll put the link in the comments section, but you may want to look at that if you have not done so already. With more and more rain forming, this further prevents ice from forming because everything is warmer, especially the waters from below. When rain falls on ice, since it is above freezing, it will melt the ice. All of these factors and others which I have discussed with you all over time, right, contribute to the declining sea ice that we are observing and measuring across the Arctic, across the polar regions. Okay, let's look at the Arctic Ocean basin as a whole. It is very likely that the 2023 minimum Arctic-wide sea ice extent was reached on September 19th. That's overall, right? We already just saw how it was about the 20th for the Chukchi and Beaufort, when in preliminary National Snow Ice Data Center analysis. That's the NSIDC. Sea ice extent, ice concentration 15% or higher around the Arctic covered 4.23 million square kilometers. This is the sixth lowest annual minimum in the 45 years we have satellite record. Most likely longer than that. Now, there's something you need to be a word of caution about the satellite data. Depending on the settings, the aperture, if you use SAR, the aperture settings and so forth, the sensitivity you program into it, a lot of times it's just going to go over and look at, what's on the surface. We'll get to that in a moment. The satellite, again, depending on the sensitivity, cannot always discern grease ice and frazzle ice from other ice. Depends on the transmittance. You cannot exactly stand on grease ice or frazzle ice. It's basically slush. And depending on the transmittance, if it has a low transmittance, it will be counted as ice covered, when I really do not consider it to be ice covered, but more transitional. Sometimes if it's in the early stages, then the satellite reading will penetrate it and will record it as open water. So one has to be really cautious with looking at the satellite data. So looking at satellite data alone is not necessarily the best idea, although it's convenient. You also need in situ observations and measurements to complement what the satellite provides. So take that caveat as you wish. So we do the same thing here now for the Arctic-wide sea ice extent, the annual minimum from 79 to 2023. Here's 2023. Okay. Right, so this is 2023 here. So we have the orange is less than 4 million square kilometers. Tan, 4 to 5. I don't know what you call that color. Bluish. 5 to 6, light blue 6 to 7, and dark blue 7 to 8, and then the smooth average. And the overall trend is that of declining ice to the point that it's a little above 4 million square kilometers. This is for the whole Arctic Ocean. We can see that again, a lot of the higher extent, higher sea ice extent occurred in the 1980s and 1990s, with the decline progressing. Well, I guess that's 5 to 6 is gray, okay. But we see the decline over the last 4 decades. The dashed line, that's this one here, plots the 2023 minimum extent. Here's 2012. And 2020 was another low year. Those are the 2 years thus far where it's less than 4 million square kilometers. And there's still some time to go here in October for 2023. But as I've shown you in the last several slides, the trend is unmistakably clear. Sea ice is declining quickly. So here is the median sea ice extent on the day of the minimum. This is the left panel for 79 to 89. Then 2023 sea ice minimum as of September 19, 2023. Okay. Ice concentration less than 15%. That's this blue stuff. Ice concentration 15% or more. Now the concentration, goes back to this earlier figure. Concentration here. It's not clear to me if they're also factoring in if it's grease or frazzle ice. But the overall point to look at is, look how much ice is here. Look how much ice is not here, right? We have a lot more open water here. You see how the ice is coming close to the Alaskan shore? Here's the Chukchi and the Beaufort Seas right here, this region. That's pretty much ice-free. Look at the East Siberian Sea. Look at the East Siberian Sea. Right? Look what's, here's the Barents Sea, right? And the Kara Sea. Look at that. Even some lost in the Laptev Seas. Ice is going away. Arctic-wide sea ice monthly extent. And again, these are departure from the average, looking at from November 78 to August 23. Okay. The 12-month average is this brick color, I guess. Okay. And the scale is standard deviations. So they're using 81 to 2010, that basically 30-year period as the baseline. So 0 means there's 0 standard deviations away from, from the mean. So if it's positive, that means there is more ice than average. Negative means there is less ice than average. And the monthly departure is indicated in this light blue with the edge highlighted in black, showing you where the exact monthly departure is. And when you look at this, starting in about 2000, the ice, for the most part, in fact, for every year, there might be somewhere increases and decreases and so on, but the ice extent is below average. In some cases, it is, 2.5 standard deviations below. Looking at about, say, 2015, 16 or so, it reaches 2 standard deviations below. Now, we have some new research, thanks to Igor Polyakov, where the role of the Arctic dipole is being found to play a significant role in controlling what happens with the sea ice. Before, it was thought that the Arctic dipole, when we initially, discovered and described it, we saw the Arctic dipole as controlling wind and airflow, and thus surface current flow in the Arctic basin, and that would either determine whether sea ice is contained within the Arctic basin or expelled out through Fram. Well, now we're finding out, thanks to Igor's latest research, that it has a much bigger role. And this, when we see going up like this over here, like in 2021, 22, 09, and so forth, that's probably the role of the Arctic dipole. I just posted a video discussing that. You may want to check that out. But still, when you look at all these things here, the ice is going away. Standardized departures are widely used as a way to compare climate and environmental data that has a significant annual cycle, and are most simply calculated as the difference between the observed and average over some reference period divided by the standard deviation in the reference period. The previous graphic is useful because it illustrates the persistence of the decline of sea ice, and that the winter ice extent recovery does not offset summer ice loss. Okay, so these are standard deviations compared to the baseline, and all this, whatever growth you may have in the wintertime, is insufficient to offset the summertime loss. Big factor is the heat coming into the Arctic Ocean in the way of through the Fram, through the Bering. The warmer waters and their persistence, right? We know that the ice melts early in the year, freezes late in the year. More open water is a higher time period year-round during the year. It's gone from 5.5 months to 7 months. The ice thickness is declining. The ice volume is declining. All these things, right? It's all happening. The figures that follow examining the sea ice in the Arctic and Antarctic and others are all courtesy of our good friend Zach Labe. So here we go. First, let's look at air temperature trends. This is degrees C per decade. So this is the couple Earth system model, and then this is the all right. So a couple of different. This is one climate model. This is observation, and you can see the models and the observations are fairly close. But what do we notice here for the Arctic? This is the annual mean that's calculated for 79 to 2022, and the thing is bloody warmer. Right? Except for a little patch, here, and basically, this is Alaska, so that's starting to head towards Prince William Sound, a little bit off the coast of Greenland. Those will be the only places where it's about average. That there basically has been no warming trend overall. But you look at the Look at the Arctic Ocean basin here. It's now these current. These are air temperature. It's warmer, up to a good degree, if not more warmer. Annual Arctic temperature taken, and the Arctic is taken to be latitudes greater than 65 degrees north latitude. Okay, so again, we have the dash blue is the is this group's observation. Then we have the ERA 5 observation, and then we have the multi-model ensemble mean. That's this white in here. The light gray is the 25th to 75th percentiles. In other words, it's the interquartile range. And then the dark gray is the 5 to 95th percentile. That would be typically a plus or minus 2 standard deviations. So, of course, we're trying to project out into the future, so there's going to be higher errors associated with that. But what we are seeing is, and this is near surface temperature anomaly. So these are departures from the baseline. And the baseline is 1981 to 2010. And this starts in 1950. And we just see what we're seeing an increasing trend. It's very clear. Now, this is for Arctic temperature, 65 degrees north latitude up to the pole. And we're seeing, look at this here, in like 2018 or so, almost reached 2 degrees C above the average for this time period. And you calculate out the mean, it is clearly showing an increasing trend. Slope of that line would be positive. And when we do the same analysis for 80 degrees north or greater, what do we see? We see that starting in about 2008 or so, with a couple of dips up above, but we're starting to see that even 80 degrees north latitude up to the pole is starting to be warmer than the 30-year baseline average. So if you start warming up the air, that's going to impede ice formation along with the warm water inputs. These are all factors that are contributing to the declining sea ice. And polar amplification. You've heard me discuss this with you before. I did a video where I even showed you a direct way to calculate this by looking at the ratios of derivatives and so forth. Again, we have temperature anomalies here, okay, starting from 1980 up to 2022, 23. And they're using the Arctic from 67 to 90 degrees north latitude, Antarctic 67 to 90 degrees south latitude. Now, the baseline is 51 to 80. And what do we see here? Okay, the blue represents Antarctica, the red, the Arctic. We see an increase for the Antarctic. So the Antarctic is warming. But look how much more the Arctic is warming. The Arctic has a higher slope than does the Antarctic. The Arctic is is a major polar amplifier here. And we can clearly see the trend. In fact, really, when you look at from 1980 to the present and compare that to the previous 30 years, 51 to 80, Antarctica, I'm looking at the fitted line here, Antarctica is warmer than this average. Yes, the graph itself shows dips above and below, but overall, when you fit the line, positive slope, it's warmer, the anomaly. Antarctica, at least up to about the mid 80s, was actually below that average of 51 to 1980. But again, we see a much higher increase such that by the time we get to the mid 2000s, even the coldest temperature is either at zero or above zero. No, it's still warmer. And you've heard me say before, what happens in the Arctic does not stay there. This spills over into the rest of the planet. Okay, so now let's look at conditions in the Arctic for September 2023. So we'll look at air temperature, sea ice extent, sea ice volume. Well, no surprise here. A clear increase in air temperature. So what the scale is, these are the years. So each of these are looking at for the month of September only. And we clearly see that September, when we look at the month of September, it's warming in the Arctic. September is basically the height of the Arctic oceanic summer. And so we have higher air temperatures that helps, a factor that helps to translate to lower sea ice extent, lower sea ice volume. You can clearly see the declining trend here. And the dot, of course, is 2023. That's unmistakable. For the sea ice extent, fifth lowest on record, ninth lowest on record for sea ice volume. And this is as of extended this out. This is looking for September, but this dot goes to, as it says here, 15 October. Annual reconstructive Arctic sea ice since 1850. So this is based on Brennan et al. 2020, and then that's in blue, and the red is Federa et al. 2017 using sea ice index. And this is now the extent in million square kilometers. The bright blue is the estimated extent. The shaded blue is the error, the confidence interval. Well, it makes sense that we're going back to 1850, so there's going to be a lot more uncertainty with the measurements and the data. So you're going to have a bigger confidence interval reflecting a larger error. And we see, once again, starting in about the mid to late 1980s, we start seeing the decline. You also notice how the error is shortened because our measurements are getting better, less uncertainty. Okay, another way of showing the extent in million square kilometers of the Arctic sea ice, looking at from September, October, November. Obviously, 2023 is still ongoing, but you can see how it is below the 2010s mean, right? Purple is the 2010s mean. White is the 1980s. Light blue is the 1990s. The little darker blue is 2000 mean. Overall, we just see it, everything shrinking down. There's less and less Arctic sea ice extent for this 3-month period over the decades. We can look now for the entire year, January through January. This hash blue is ice-free, it's all open water. The dark blue, right here in the middle, that's the median based on 81 to 2010. The this blue here, a little darker blue here, that's the interquartile range, the 25th to 75th percentile. The light blue is the 10th to 90th percentile. And then the gray is plus or minus 2 standard deviations. Current year is in red, 2023. We see that over the year for 2023, it's in the the minus 2 standard deviation realm for most of it, which would, for most part, pretty much a significant result. And then starting in mid-August or so, but definitely through September, it is outside the 2 standard deviation, below the median. And it's just now crept back up into 2 standard deviations below. But we're seeing that 2023 is shaping up to be a low sea ice extent year. And then we can just look at the anomalies. So the horizontal line right here is the median. So this is the million square kilometers. So this would be the median. So there was more ice than the median, less ice than the median. And 2012 is this yellow right here. And then 2023 is the red. As you can see, there's just less ice. Okay, there we go. Okay. So now, let's look at the Arctic Sea Ice anomalies. Another way of presenting this, but now we're looking at it from 79 to 2023. Blue is more ice. Red is less ice. Horizontal white is the median. What do we see starting at about 2004 or so? Most of the ice is below the median. Anomalies are calculated using a 5-day running mean from a climatological baseline of 81 to 2010. And it was updated as recently as the 20th of October of this year. So this is the Arctic Sea Ice extent anomaly stretching from January 79 to present day. Ice is going away, folks. And if we want to look at the Beaufort, the Chukchi, East Siberian, Laptev, and Central Arctic. So it's not including the Barents, not including the Kara, okay? Not including the areas in the Canadian archipelago, like around Nares Strait and so forth. We see that 2023 is one of the lowest years. And it makes sense that September, October is when you get your minimum, as that's oceanics summer. Now, here is a breakdown by region. I really like this graphic. You can see in a snapshot what each region is doing. And when you see something like for the Barents, it zeroes out. Right? The Chukchi is pretty much zeroing out. And we can clearly see, and again, 2023 is in red. The yellow is 2012, the other low year. But we can see what this year is going on all across the Arctic. It's turning out to be one of the low sea ice here. Laptev, not so much because the Atlantification process hasn't quite reached it yet. And the Kara is on its way. So this is really nice, showing by region. And then the same thing, but showing the median and this bluish grayish being plus or minus 2 standard deviation. And we can see in a lot of it, a lot of these regions, pretty much out of the 2 standard deviation, like for example, the East Siberian Sea, or at the very bottom of it. So this is proving to be a significant low sea ice year. So all these, that's what this all is indicating. Now, let's look at the average sea ice extent for October. 1985 here on the left, 2022 on the right. Still compiling data for 2023. What do we notice here? A bit more ice here, not so much ice here. You notice, okay, here's the Chukchi and the Beaufort right here. East Siberian is over here. There's no ice. There used to be ice. In fact, in the depths of wintertime, it actually extends out into the Bering Sea. There is no ice here. And if you look, like here's Novaya Zemlya, right? Some of the islands here, less ice on the southern edges of those places. So now let's look at the sea ice concentration trend. That's a percent per decade. Okay, calculated from 79 to 2022. The dark brown is less ice. The blue is more ice. Do you see any blue here? No. Look at, right, Beaufort, Chukchi, East Siberian, Laptev, Kara, Barents. What do we see going on here? Anywhere from 15 to 25% decrease per decade. This is absolutely amazing. Biomass data is looking at sea ice thickness. So this starts giving us a hint as to how much multi-year ice persists and ice volume. So we have the thickness. If you have this black here, that means there's no ice. And as we trend towards white, you're getting thicker ice. So this is looking at September of 2023. So that's on the left here is the actual measurement and thickness. Not a lot of thick ice here, folks. Very rarely do we get to some 2 meters thick or higher. And that's pretty much in the Canadian archipelago. The rest of the Arctic Ocean, we're not seeing great ice thickness. So what is the anomaly? Again, looking at 81 to 2010, we're seeing a 1 to 2 meter decrease. Just look at this. This is a lot of decrease in ice thickness. And even into the Canadian archipelago, we're starting to lose the ice there. This is very troubling. So this is the based on Zhang and Rothrock, sea ice thickness and anomalies, updated for September 2023. Arctic sea ice volume by year. Here's 2023, kind of at the bottom of the pack. But once again, okay, it's cyclical, right? Seasonal. But look at what we see by decade. It's just less and less ice thickness. And this is usually measured in cubic kilometers. You get down here, we're basically talking what? Some 1,000 cubic. So we have 3,000 cubic kilometers. It used to be 30,000 cubic kilometers. Basically, an order of magnitude of ice volume has been lost. This is crazy. Okay, so previous one was volume, and then we can look at the thickness. We see the same trend, less and less by decades. Here's 2023. This is in meters. Right? So we're going from like 2.75 or so, 2.6, down to about 1. More disturbing trend. And looking at a couple of biomass data sets, Arctic sea ice volume in September since 1901. And we have some cyclical aspects here. We can see this dashed line is the average, the median. And again, what do we see? Starting in about the 1990s or so, whoomp, it drops. Now, you can also make the argument, and I do make the argument, that a lot of that has to do with a significant increase in ocean heat content, melting the ice from below. And that's why I made the comment earlier, it's like someone's flipped the switch. You heard me argue. The planet went past the tipping point in the mid-1990s. One of the manifestations of this tipping point is the loss of sea ice. The volume of Arctic sea ice is decreasing. Annual maximum, annual minimum, right? Note the difference in the scale, both using volume, 1,000 cubic kilometers. So annual maximum, this is like March, the oceanic winter, and then minimum like in September. Going from 79 to 2023. And what do we see? Quite a drop. Very negative slope here. And now let's look at Antarctica. Antarctic sea ice, 2023. Even at the other end, 2023 is proving to be a significant low sea ice year. This is looking at extent, so 1 million square kilometers over the year. Now, September is the oceanic winter for the southern hemisphere. And look what the departure is from the rest of the years. This is such an amazing drop. And it started early. It started early and just dropped. I did a video explaining the role of ocean heat in influencing this. And now we look at it with the median, the interquartile range, the 10th to 90th percentile, and then plus or minus 2 standard deviations. 2023, except for tickling minus 2 standard deviations in like April or so, is off the chart. It doesn't even reach the statistical ranges. It does not reach any of these percentiles. It does not reach minus 2 standard deviations, aside from this little location there. This is nuts. Very significant. Okay? And now looking for 3 months, period from September through November, Again, it's not even in the groupings with the others. 2022 is this yellow. Even if that was one of the lower sea ice years, it still was at least in this bunching. It would still be located within all this statistical shaded regions. And then bang, 2023. This is their winter down here. And if you're losing the sea ice, then you don't have that buffer against the land ice on Antarctica, making it easier for the land ice to calve off and get into the ocean. Currents take it into warmer, lower latitudes, warmer waters where it melts, adding the sea level rise. Again, these are the anomalies. And my word, really, there are no words to describe this. Look at it. This is just nuts. Again, except for in April, in the early part of May, it's not even in the grouping. These are departures. It's well below the departure. Departures are calculated as a 5-day running mean. Okay, so these are million square kilometers. So this would be like, for example, if I look in July, that's about 2.6 million square kilometers below the average. That's a lot more open water. And then you do the same breakdown as I showed you earlier for the Arctic Ocean, the Bellinghausen, Indian Ocean, including Indian Ocean, Pacific Ocean, the Ross Sea, and the Weddell Sea in 2023. Now it's interesting, in the Bellinghausen, 2023 is pretty much found in the middle of everything else. The Ross Sea has started out in there, then it kind of dropped out. Indian Ocean, sort of at the bottom, low end of things. Pacific Ocean, it's in the grouping, but at the low end of things. The Weddell Sea, for most of it, falls out of the other grouping. So now how does that compare when we look at it statistically? Well, when we look at it statistically, we see the Weddell Sea outside plus or minus 2 standard deviations. The Ross Sea within falls out a little bit. The Indian Ocean within tickles at the -2 line. Pacific Ocean pretty much within, nothing significant there. Weddell Sea, I would say nothing significant here. Excuse me, got myself mixed up. The Bellinghausen, nothing significant there. Pacific Ocean, nothing significant there. The Weddell Sea, we have a significant loss. And the Ross Sea, significant in like about August, September or so. There you have it. Now let's look at Antarctic sea ice volume. 2023 is in yellow. And looks like it was just pretty much only one other year that had a lower volume than 2023. So, to wrap this all up, finish. Yeah, a lot of slides we went through. You can tease out, when you, for example, you look at these, departures, okay? These are, you read your scale, million square kilometers, 1 million square kilometers below the average. That's how you would read those, something like that. Okay? These are just data, okay? So when you see something like this, okay, this is giving you how it compares statistically. Again, this is just data. You can look at the raw numbers, if you will. And we can calculate the slopes and so forth. And these are the departures. So it's like 1 meter below, 1 meter less thick than the baseline average. And again, same thing with all of these. You can just look at comparisons and how it compares. So when we're looking at the extent in million square kilometers for the Arctic sea ice anomalies, if I'm looking at this value here for say 2013 or so, and it's -3, that's what? It's 3 million square kilometers less ice than the average for the time period under consideration, 81 to 2010. So that's how you would, look at these graphics. Again, an average, so this is below, and again, -1, that's 1 million square kilometers below the average. 1 million square kilometers above the average, etc. So what do we have here is that we are losing the ice at both ends. Now this one just looked at sea ice. So we're losing the sea ice at both ends. I've discussed with you a number of reasons why that is. We have the warmer waters inputted in through the Arctic Ocean via Fram and the Bering. We have warmer air temperatures. I showed you that. The ice freezes later in the year, it melts early in the year, so there's more so the period of open water increases. The ice volume is decreasing. The ice thickness is decreasing. Turns out this is true at both poles. For the Arctic Ocean, in a previous video, I discussed how the Arctic dipole is now turning out to be an influencing factor in the sea ice extent when it freezes and so forth. That it could be moderating a bit, but it does not offset the overall trend, which is declining sea ice. For the Antarctic, I did a prior video where I explained the ocean heat, what flows from the Pacific and Indian Ocean, are melting the sea ice and even under the land ice that cantilevers out in the Antarctic region. But overall, it's the massive ocean heat content that is, in my view, a major driver of what we're seeing. We now have, since for about 50 years or so, that the oceans have absorbed more than 400 zettajoules of energy. And those zettajoules of energy, because of the increased stratification, and you can't sequester the heat to death, is now being returned. And it's being returned in powerful hurricanes, lots of excess heat and moisture to the atmosphere, causing a precipitation bomb and melting sea ice. Overall trend, we're losing the ice at both ends. Of course, a number of factors. I cite ocean heat as a major one, adding to the Earth's energy imbalance. So there's your update. I hope you found this informative. And, please support me on Patreon or buy me a coffee. So until the next time, thank you for your time.